Quad means square, so when we have a quadratic equation or quadratic function, this means that the variable, normally x, will get squared. A quadratic equation is an equation of degree 2. And the basic parent function is y equals x squared, and it's quadratic because this x is squared. This is a graph of what y equals x squared looks like. This shape is called a parabola. All other parabolas or quadratic functions can be obtained from this parent function y equals x squared plus one or more transformations. A transformation can be a translation up or down, a reflection, or a stretch or compression. Let's start with translations. So we have our parent function, which is y equals x squared, which is displayed in black on both sides. When we have a vertical translation, we're either moving the graph vertically up or down. In this case, y equals x squared is our basic parent. So we have plus 4, which moves the graph up 4 units in this red right here. And we have y equals x squared minus 6, which moves the graph down 6 units. So this plus k is how much we're moving the graph up or down. As you can see, the shape is the exact same, it's just you're moving it up or you're moving it down, depending on what your k constant is. So this vertical is moving it up or down, and horizontal is moving it left or right. So for this, we have x minus h squared. And our parent function, like last time, is also y equals x squared. So basically, for x plus 2 squared, we're moving the graph left 2 units, so it's this red right here. And for x minus 3 squared, we're moving the graph right 3 units. So for this one, as you can see, we have to adjust it based on h. So as you can see, the shape is still the exact same. It's just you're moving the entire graph left or right based on h. Now, let's go over stretches and compressions. Let's start with the vertical stretch or compression. So vertical means that we're going towards or away from the x-axis. And we have y equals a times x squared, where a is going to be our constant. If the absolute value of a is greater than 1, it's a stretch. If the absolute value of a is between 0 and 1, it's a compression. The reason we care about the absolute value is because we care about the magnitude of the number. If it's negative, it's still going to be a stretch or compression. There's just going to be reflection in there as well. So here we have y equals 4 squared, which is a vertical stretch because it's greater than 1. And the red is drawn here. And our vertical compression, y equals 1/5 x squared, is this blue graph that we see here. The vertical stretch is going to appear thinner. And a vertical compression is going to appear wider. Next, we have horizontal stretch / compression. Horizontal means that we're stretching or compressing away from our y-axis. So in this case, we have y equals a times x squared, and this a is inside the parentheses. So this really becomes a squared times x squared. So when we have absolute value of a is greater than 1, it's a compression by a factor of 1 over a. And 0 to 1, absolute value is going to be a stretch by a factor of 1 over a as well. So when we have y equals 1/4 x squared, it's a horizontal stretch. In this case, as you can see, it's this blue right here. And our horizontal compression is y equals 4x squared in this red right here. As you can see, vertical stretches and compressions and horizontal stretches and compressions can look kind of similar to each other, but the way you tell what kind it is by whether this a or this constant is inside squared or outside. Now, let's discuss reflections. So we have reflections in the x-axis first. In this case, we flip the graph over the x-axis, which is right here. As you can see, we're kind of flipping it upside down. So this becomes y equals negative x squared. So we're just putting this negative right here. We're putting it outside this parent function of x squared. So all the positive values now turn negative. And our blue one is our reflection, and the black one is our parent function. Now, for this one, we have reflection in the y-axis. In this case, we're flipping the graph over the y-axis. The y-axis is this axis right here, and we have y equals negative x squared. In this case, the negative is on the inside, which cancels out because negative x times negative x is equal to x squared, which is the exact same as our parent function. So here the graph is in blue, but it's also the same graph as the black one. So the parent is reflected over the y-axis, but because y equals x squared already has y-axis symmetry, it looks the same and the reflection changes nothing. We've gone over translations, compressions and stretches, and lastly reflections. When we went over them, we only did one transformation to the parent function at once, but know that these can be combined. For example, you can do both a translation and a reflection, you can do a compression and a reflection, and so on. The roots of the quadratic equation are the values of the variable, normally x, that satisfy the equation. By satisfy the equation, we mean makes y equal to 0. These are known as the solution or zeros of the equation. So here we have y equals x squared minus 1, and we want to find the solutions. Like I mentioned, we want the values of x that make y equal to 0. The y equal to 0 is on the x-axis right here. So where the graph hits the x-axis, we have our solution. In this case, it hits it right here at negative 1 and right here at 1, which means our solutions are x equals negative 1 and x equals 1. We should be able to check our answer and plug these in, and it should give us 0. Let's do that now. Y equals negative 1 squared minus 1, which is equal to 1 minus 1, which is 0. We know x equals negative 1 is correct. Let's check the second one. So y equals 1 squared minus 1 equals 1 minus 1, which is equal to 0. So we know x equals negative 1 and x equals 1 are both the correct solutions. Now, let's take a look at this one. We have y equals x squared. Same as before, we want y to be equal to 0. Let's look at this graph we have right here. So, the solution is going to be where it hits the x-axis. As you can see, it hits it at one point, right here, 0, which means x equals 0 is our solution. And let's plug it in just to check. Y equals 0 squared, which is equal to 0. We know x is 0 is our solution. Now, let's go over the standard form for a quadratic equation. Quadratics can be written in many different forms. As long as there's like a variable like x that's squared, it's a quadratic. But this is the standard form. Ax squared plus bx plus c equals 0. A, b, c are going to be known in real values, so they're going to be our constants. A can't be 0, and x is the variable or something that's unknown. So here is an important thing. A, b, and c are constants, and they can be any number, but a cannot be 0. And the reason why a can't be 0 is if a is 0, then it's 0x squared plus bx plus c equals 0, which translates to bx plus c equals 0. We no longer have our x squared term, so it's no longer quadratic. So b and c can both be 0, but a cannot be 0. Now let's do some practice identifying quadratics. First, we're going to verify whether something is a quadratic equation. If it is, we're going to find a, b, and c. So let's start with this one. Our standard form is on this right. Ax squared plus bx plus c is 0. And we have this. Is this quadratic? Yes, it is quadratic. We have ax squared plus bx plus c equals 0. It matches perfectly. We have a is 3, b is 7, and c is negative 4. What about this one right here? We have x squared equals 6. Let's move this 6 over so it equals 0. It'll be easier to tell then. Squared minus 6 equals 0. Is this quadratic? Yes, it is quadratic. We have the base form is still ax squared plus bx plus c equals 0. As you can see, we have a equals 1. Bx, we don't have any x, so b is equal to 0. And we have c is equal to negative 6. As long as a is not 0, we're okay. Like I mentioned, b and c are both allowed to be 0. Now, let's do 2 more practice problems. Is this a quadratic? 5x minus 3 equals 0. No, it's not a quadratic. It's not a quadratic because there's no x squared term. But another way of looking at it is that if we write this out, x squared plus bx b equals 0. A equals 0 because there's no x squared term. B equals 5. And c equals negative 3. But like I mentioned, a cannot be 0 quadratic. Because the x squared term is what makes something quadratic. What about this one on the right? 1/2 x squared plus 8x minus 5 equals 4. Is this quadratic? Yes, it is, because there's that x squared term right there. But let's move this over so we can identify it properly and make it equal. This is 1/2 x squared plus 8x minus 9. We subtract 4 from both sides to make this side equal 0. So now, we have a is equal to 1/2, b is equal to 8, and c is equal to negative 9. It's still quadratic because a is not equal to 0. We've reached our final challenge question. Now, we want to know whether 2 over x plus 3 equals x plus 4 is a quadratic equation. If it is, we want to identify a, b, c, and we want to know whether negative 5 is a root. So let's start with the first question. This makes it kind of hard to tell. We want to see whether it looks like the standard form. So let's multiply both sides by x plus 3 to move this out of the fraction. So for negative 1, I'm going to do 2 plus 3 equals x plus 4. We do 2 equals x plus 3 times x plus 4. Okay. Now we're going to use FOIL to multiply this out. First, x times x, which is x squared, outside, which is x times 4, going to be 4x, inside, which is going to be 3 times x, which is 3x. And lastly, we do last, which is 3 times 4, which is going to be 12. So we simplify. That's going to be 2 equals x squared plus 7x plus 12. We want a 0 on this side, so we're going to subtract 2 from both sides. That gives us x squared plus 7x plus 10 equals 0. Now that we have x squared plus 7x plus 10 equals 0, is this a quadratic? Yes. Yes, it is. Yes. Quadratic. Now let's find a, b, and c. So we have a is equal to 1 because there's 1x squared here. We have b is equal to 7. And we have c is equal to 10. Now, let's check whether negative 5 is a root of the quadratic equation. To test whether negative 5 is a root, we plug in negative 5 for x here. There's 2 ways we can check. We have 2 over x plus 3 equals x plus 4 as our equation. X squared plus 7x plus 10 is also the same equation, just rewritten. We can plug in -5 to either or both and get our answer. Let's do both. For this one, we have 2 over x plus 3 equals x plus 4. Let's plug in -5. We get 2 over -5 plus 3 equals -5 plus 4. This gives us 2 over -5 plus 3 is -2 equals -5 plus 4, which is -1. We get -1 equals -1. So we know that -5 is a root because this is true. However, we can also plug it into this equation and we should get 0. So let's do that. So we have x squared plus 7x plus 10 equals 0. We have -5 squared plus 7 times -5 plus 10 equals 0. We have -5 squared, which is 25 because the negatives cancel out when there's 2 of them. And then we have 7 times -5, which is 35. We have plus 10 equals 0. Have -10 plus 10 equals 0. 0 equals 0, which means that -5 is a root. And that's the end of this video. Thank you so much for watching.